question is going to be, I assume we're solving for x. The question is 3x plus 19 equals x minus 13.
Okay, I was setting some stuff up on my computer to maybe help with a visual for that. So if you want to come on over to my screen, I think I got it set up here.
Oh, wow, are you busting out the algebra tiles?
I am.
Wow.
I love these. Oh, I think my thing's upside down. Uh-oh. Hang on. There we go. Okay, we're good. So we have 3x plus 19, oops, okay, there we go, is equal to x and then minus 13. I'm going to just double check my 4, 8, 10, okay, 19 and then 13. Good. Okay, so what I set up here is maybe a visual of how we can possibly try to solve this equation. Now, I'm using Algebra Tiles from the CPM curriculum, which there's a lot of background knowledge involved in it, but I think is really nice if you are new to solving equations. So I'm going to kind of run through the background information pretty quickly so that you know what I'm doing. So what I set up, so this is an equation mat, and what I set up is the 3x. You kind of can see these little bar tiles over here. Those are x's. And then the 19, each of these like little 1 tiles, that all adds up to 19. And then we're assuming that what is on this side of the mat, the value is equal to what's this on this side of the mat. So I've got 13 little negative, oops, I turned that one positive. 13 little negative tiles, and then I have my 1x there. So you can see that's the equation I have set up. Now, the whole idea with equations is that, or the assumption is that what's on one side has the same value as what's on the other side. And what we're trying to figure out is what is that value of x that is going to make both of these sides equal to each other, that have the same value. One of the ways that we can do this and easily see what the value of x is if we isolate x. Let me give you a very basic example here. I don't want to mess up my algebra tiles, but I'm going to draw one next to this. So let's say I said on this side, I have 1 x tile, and then I have 5 tiles here. What we're trying to figure out is what must this x value be in order to make this balance, make these the same. So in this case, it's really easy to see that, well, okay, if x were 5, then we'd have the same thing on both sides. So that's what we're trying to do, is if we can isolate x, get it by itself, then we can figure out what it is to make both sides of them equal. Now, with the assumption that that both sides are equal, think of it as like a scale. I keep putting my hands out like this, but think of it as like a, one of the scales, the justice scales, right? That those old time scales that are actually measuring weight, that if it's heavier, it tips, right? And think of the properties of that. If you have a scale and you take the same thing off of both sides and it's balanced, it's going to stay balanced. Same goes if you add the same thing to both sides. It's going to stay balanced, hence stay equal. So those are some things that we can do. We can take away things that are the same from both sides, or we can add things that are the same from both sides. Now, that being said, if I can follow those rules, I'm keeping the integrity of my scale, right? So what I can do is, if I want to get all of my x's on one side and everything else on the other, meaning get x by itself, what I can do is a tricky move like this. I can add a negative x to both sides. So I just added the same thing to both sides. And then what happens is, if I have a negative and a positive, so I just kind of highlighted that together. Think of if you have $1, but then you spend $1, you're back to 0. It's called a zero pair. They cancel each other out. You've probably heard us say that a lot on the show. So these guys cancel each other out. And then these guys also cancel each other out because they just equal 0. So now I'm left with a slightly simpler equation. And the traditional algebra that you've probably seen, it works kind of like this. I'm subtracting x from both sides. It's gone over here. Now on this side, I just have 2x plus 19 is equal to negative 13. So you just saw me do that there physically. Now, to get x by itself, I have to deal with all these little 1's here. I have all these little 1's that are in the way of me figuring out what x is. So think about it again, is I want to cancel those. I want to get rid of them. So if you think about what I can add to both sides to get rid of them, is I can just add their negatives. So if I have 19 of them here, if I add 19 negatives to both sides, that's okay because I'm keeping my scale balanced, they would cancel these out. So here, I'm going to try to see if I could do this kind of quickly. So all of those there, you can kind of see I've got 19 of them there. I'm going to just make them all negative real quick. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And then I have to do the same thing and add the same thing there. And I should have just did them. Hang on. We'll do 8 at a time. I'm going to add 19 negatives here. There's 8. There is 8 more, so that's 16. And I just need 3 more. Can't really get 3 easily. We'll add 4 and get rid of 1. Okay, there. And then I gotta just make them negative and then get rid of the 1. So I just added negative 19 to both sides of my equation. That way I'm getting my x's by themselves. So now these all cancel because of my positive 1's and negative 1's. They're gone, and I'm left with 2x on this side and then negative 19 plus that negative 13 on the other side. So here's what I did algebraically. Minus 19, I had negative 19 to both sides. Those canceled, I just have the 2x, and then over here we have, if you were to count them, and I'm not going to count them, but you have negative 32 over there. So now what you can kind of see is that we could divide these negative 1's evenly among our x's to see what each x is. So if we have 32 of these negative 1's, it's going to end up where we have 16. Let's do one more row here. 16 negative 1's with each x. You can see that over here. So there's an equal group. There's an equal group. You can see that if each of these x's were to equal negative 16, that it would maintain the integrity of the scale, and both sides would then be equal. So what I did, and this is back to traditional algebra, is I divided my x's into 2 equal groups, and I divided my 1's into 2 equal groups. And I was left with each one of my x's equaling negative 16. Now that was kind of a long way to solve the problem. Typically, you would just do what I was doing on the right there with all the algebra and writing that down. But I wanted to show visually what is happening when you're solving equations, so that maybe you could understand what we're doing when we're solving for x and why we're doing it. So
yeah,
hopefully
I think
that
that's you explained it to me earlier this year, and I never used the Algebra Tiles before.
Mm-hmm.
So they're a little confusing at first, but they really give you a good visual of like what's happening. Since some of you are visual learners, it's helpful.
Very true. Very true.